Chapter 12, Analysis of Variance. In this video, you'll learn about analysis of variance, also known as ANOVA. In addition, we'll conduct the related hypothesis test and post-analysis of variance pairwise comparison procedures, also known as the Tukey-Kramer test. In chapters 9 and 10, we learned how to conduct hypothesis tests for single population means and two population means. In real-world application, we might have to compare the means or averages of three or more populations. This is when we would have to use one-way analysis of variance, or ANOVA. Here, the hypothesis test states that all the means are equal, and the alternative hypothesis states that the means are not all equal. For instance, I teach 4 sections of business statistics. My null hypothesis would be that the average final exam score will be equal for all my 4 sections, which are our 4 populations. The alternative would be, if I have enough evidence to reject the null, would suggest that not all of my sections' average test scores will be equal. It could be that all 4 sections have different averages, or perhaps 3 sections have the same average and 1 section is different, or it could mean 2 sections have the same average and the other 2 are different. There's a variety of combinations possible, but whatever that is, it simply means that not all 4 sections have the same average on the final exam, if it turns out that my alternative hypothesis is true. So let's look at if our null hypothesis is true. This is where all of our means are equal, so you can see them lined up right here. There are some assumptions to be aware of with a one-way ANOVA. It assumes that our populations have equal variances, our observations are independent. So in our example with our test scores, one student's test score in a class is independent of another student's test score in a different class. Our populations are normally distributed, so they're bell-shaped. And the data that we're looking at are interval or ratio. Remember, this just means numbers that we can measure. So test scores, for instance, are ratio. Now let's say if our null hypothesis is false, not all the means are equal. So again, here are our 4 class sections, for instance. Even if the null hypothesis turns out to be false, our assumptions still apply. We still have equal variances, the observations are independent, we're working with normally distributed populations, and it's still ratio level data. But we can see here that our means are all different. So if our null hypothesis is true, that means our populations have identical distributions. Recall in Chapter 7, we learned about sampling distributions, where if we took many samples and find each sample's mean or average, and then graph them, we get a normal distribution or bell-shaped curve. So if we were to take samples from each population and graph their means, the distribution should be close in value, and we'll learn how close means shortly. Now, if we end up rejecting the null, that means that our sample means are substantially different from each other, although some pairs might be the same. So that doesn't mean all our means are different, just means that at least 2 of them are different. And we'll learn how to determine which samples are substantially different. Before we learn how to conduct an ANOVA, we should understand some of the key concepts. The first is a factor, which is our independent variable, or the variable that might explain the variation in our dependent variable. For instance, the factor for my 4 sections' final exam scores might be when the test is administered. So for example, our class is online, so you can take the exam at home when you want. I have one section that takes their exam on a Tuesday morning, another section that takes their final exam on a Monday morning, and a different section that takes it on a Wednesday afternoon. So perhaps I want to see if the time of day impacts students' performance. Next is levels. The level is the categories, measurements, or strata of our factor of interest. In other words, it's the number of populations we're studying. So using my example, the 4 sections of business stats would be our levels. A balanced design means that our experiment has the same sample sizes. So let's say I take a sample of 10 students from each of my sections in order to do a balanced design one-way ANOVA. We also need to understand the idea of partitioning the sum of squares. To partition the sum of squares, we're dividing things up. So first, we have our total variation. This is the aggregate dispersion or spread of data values across all our groups. So for instance, if I look at my 4 sections, sample of 10 scores in each section, we'll see variation in the test scores at a high level. When we're looking at between sample variation, this is if I take the average from each sample of my 4 sections and compare how the group averages look. So I'm comparing the class averages. And within sample variation would be when we're examining a particular section. Say I look at our online section, there will be variation in the 10 students I sampled for their test scores. So potentially we could have a lot of variation going on, variation between groups, as well as variation within groups. And then our total is all of that combined. So let's apply our understanding of these concepts to one of the homework problems you'll do. This is number 13 in the textbook. You are responsible for installing emergency lighting in a series of state office buildings. Bids have been received from 4 manufacturers of battery-operated emergency lights. So often in business, before an organization awards business to a company, they will often bid it out to multiple companies to see who has the best product or the best deal. Here we see that the costs are about equal, so the decision of who to award the business to will be based on the length of time the lights last before failing. This is because we want lights that last a long time. A sample of 4 lights from each manufacturer has been tested with the following values, which is the time in hours that our emergency lights last, recorded for each manufacturer. So we have manufacturer A, B, C, and D. And we have a sample of 4 emergency lights from each manufacturer. I like this problem because it reminds me of when I used to work at UCSD, which is a public university. So anytime we had to buy anything, we had to bid out the projects publicly to potential suppliers. That way we could make sure we got the best deal in terms of quality of product and price. So first we want to describe the parameter of interest in our story. What we're interested in knowing about our emergency lights, and in order to determine who might win the bid, is that we're going to evaluate our emergency lights in terms of the time and hours those lights last before failing. In other words, the longer lasting the emergency light, the better. Next, we want to identify the factor associated with this experiment. Recall that the factor is the independent variable that might affect the dependent variable. In this case, the dependent variable is the time and hours. So in this story, the manufacturers of the battery-operated emergency lights is the factor. Because while all 4 companies are providing battery-operated lights, the manufacturers themselves are different. Imagine buying a car. I can buy a sedan, but the car manufacturers like Ford, Toyota, Honda, and Chevrolet are different in how they make their cars, which can in turn impact the performance of the car. In part C, we have to identify the levels. Remember, this just means how many populations we're studying. So if you're following on the worksheet, you can double check how many manufacturers are we looking at. We see that there are 4 manufacturers. Therefore, we have 4 levels or populations that we're examining. Type A, B, C, and D. Now, we should also discuss the degrees of freedom that we need for our ANOVA. So in part D, we're going to find the degrees of freedom for our between sample variation. So think of it this way. I'm comparing between my groups or my samples. So that's where I'll take my K, the number of groups or populations I'm studying, and minus 1. So since we're studying 4 manufacturers, we'll take 4 minus 1, which equals 3. For our degrees of freedom for within sample variation, that means I'm looking at the variation within each of the manufacturers. So we're going to take n sub t, which n sub t means the sum of our sample sizes. So if I add up all of my sample sizes, or I count them, we can see that there are 16. And then we will subtract the number of populations we're working with. So when I add up all my sample sizes, I get 16, and then I'll subtract the 4 populations that we're working with, and that gives us the degrees of freedom of 12. And then in part F, we also need to know the degrees of freedom for our total variation. This is simply our sum of our sample sizes, which we know is 16, and we'll minus 1. So 16 minus 1 gives us 15. Note that when I add the degrees of freedom from my between sample and within sample variation, which is 3 plus 12, I get my total variation degrees of freedom of 15. Let's go through the logic and process of ANOVA. We will reject the null, which states all our means are the same, if the variation between the sample means between my groups is large relative to the variation within the samples. So using our final exam scores as an example, if the variation across the sampled final exam averages of my 4 sections is very different in comparison to the variation in scores within each class section, we would reject the null and our class averages are not equal. So for step 1, we have to find the sum of squares. That's our SST, SSB, and SSW. So the sum of squares total, the sum of squares between our samples, and the sum of squares within our samples. And Excel will do this for us. In step 2, we will convert the sum of squares into variance estimates. To do this, we'll take our sum of squares between and divide it by the degrees of freedom. So again, sum of squares between, this is where we're looking at our groups. So that's why we'll divide it by the degrees of freedom as it relates to our groups, k minus 1. Then for the mean square within samples, what we'll do is we'll take our SSW, our sum of squares within, and divide that by the degrees of freedom. So again, within samples is I'm looking at the data within a particular sample or grouping. So that's why we'll divide it by the degrees of freedom of all of our sample sizes minus our k. We'll see how to read this in Excel shortly. If the null hypothesis is true, with our population means being equal, then MSB and MSW will also be equal, except for the presence of sampling error. So really, it just means that these two numbers will be close together. However, the more our sample means differ, the larger MSB will become. Therefore, for step 3, we're going to check the relationship between our MSB and MSW. To do this, we will take MSB and divide it by MSW to get our F test statistic. Because, for example, if the two numbers are the same or very similar, when you divide two numbers that are the same, you get 1. So it's not very big. However, if our MSB is very large, and when we divide it by MSW, if our F test statistic is greater than our F critical value, we would reject the null. Note that here is our distribution for this particular test, and it goes left to right. We've been learning about critical values for several weeks now. We learned Z critical values and T critical values. So now we're adding one more, and it's called the F critical value. Critical values are just the cutoff points based on our alpha to decide when to reject the null. So here, for instance, would be our F critical value. And so if our F test statistic that we get by taking MSB divided by MSW is greater than or on this right side of our cutoff point, we will reject the null that the populations have equal means. In other words, our means are not equal. Here's how it looks in Excel. Once we run the ANOVA, we get a table of data that we need to understand how to interpret. So here are labels of our variation. It's between samples or between our groups, within samples, within each group, and then the total. So in the second column, this is our sum of squares. This is where we get our SSB, SSW, and SST. And recall that when I add SSB and SSW, I get SST. Our degrees of freedom that we calculated earlier in our problem 13, this is stated right here, where I've got k minus 1 for between samples, my n sub t minus k for my within samples, and my n sub t minus 1 for my total. And then in this column is our mean squares, where MSB is our mean square between, and our MSW is our mean square within. You'll see that when I take SSB divided by the degrees of freedom, we'll get MSB. And same thing, to get MSW, I'll take SSW divided by my degrees of freedom and get the MSW. Then to get our F test statistic, we will take these two numbers and divide them. So that's how the data works across our cells. So our decision rule is that if our F ratio, or our test statistic, is greater than our critical value, we reject the null. Now, we can obtain our critical value from Excel or Appendix H. I'm just going to show you how to do it in Excel. So we're going to continue with problem 13 from the homework. We'll go ahead and conduct our One Way ANOVA. Now, remember the data here will be different from the data in your MyStatLab homework, but it's good to practice to see how it works before you try the homework. So part A gives us our instructions that we're going to be using a significance level of 0.01. It asks, what conclusion should you reach about our 4 manufacturers' battery-operated emergency lights? So here on the right are the instructions to run our ANOVA single factor, and the instructions are also on the worksheet. We'll go ahead and run our ANOVA by going to Data, Data Analysis. ANOVA single factor is actually the very first tool. We'll click OK. For our input range, you'll just select all of the data. And I always recommend selecting the labels as well so that when our data comes out in the tables, it's nicely labeled for us. So we'll make sure to check labels in the first row. The alpha in the story was 0.01. And then we'll go ahead and click OK, which will take you out to a new tab. But for me, I like to keep it on the same page, so I'm going to click Output Range and then tell it to put it just below our data right here. And then click OK. So here is our ANOVA single factor. And I like to format my numbers and move my decimal places over just so they're consistent. This will also help you with rounding issues. So if I increase or decrease our decimals, I'm now in the hundreds place, for instance. And then same thing here, I'm going to just format my decimals just for consistency so it's nice and clean and easy to read. So in the Excel tutorial file I provided, I've also included a tab that says how to read ANOVA. So if you click on that, I have the ANOVA example that we just ran, and I've included in red the explanation or the names of each column or row that you're looking at. So you can use this as a point of reference if you forget what an acronym or a word means in terms of the data. So bringing our data back onto our slides, we will now compare the F test statistic to our F critical value. Here's our critical value, F crit. Again, here's where we get it from Excel, or you could have looked it up in Appendix H if you wanted. And here's our test statistic. Just like we've been doing for the past several weeks, we need to make a conclusion based on these two numbers. Note that you can also do the p-value approach, where we will compare the p-value to our alpha. If our p-value is less than our alpha, we will reject the null hypothesis. But let's go ahead and conduct our hypothesis test using the critical value approach. So our critical value, or our cutoff point of 5.9525, is right here. And that's based on our alpha level of 0.01. If the story had asked for a different alpha level, we would have a different F critical. The null states that all 4 manufacturers have the same time frame on the emergency lights, and the alternative says, no, they're not all equal. So our F test statistic that we found in Excel was 10.48326. We can see that it is to the right of our critical value. So since our F test statistic of 10.48326 is greater than our F critical, which was at 5.9525, and because our p-value is less than our alpha, we can reject the null hypothesis and can conclude that at least 2 population means are different. I don't know which ones are different, but at least 2 of them are.